Hello, good morning everyone. Today I am going to teach you organic synthesis, and as you all know, synthesis is an art. Synthesis is an art, and chemist is an artist. Yeah, chemistry is an artist, and organic synthesis involves the art of building new molecules. Okay, why we have to build new molecules? Because new organic molecules are very much essential as for they are used in pharmaceuticals as pharmaceutical intermediates and for variety of purposes, for building many other new molecules and for research purpose also. So this art involves, and as I told you already, it's a branch. Organic synthesis is a branch of chemical synthesis involved in the construction or synthesis of organic molecules. So why we have to synthesize organic molecules? Because they are used to synthesize a variety of natural products, new organic molecules, drugs, drug intermediates, that is pharmaceutical intermediates, and a variety of other industrial intermediates, and which are used which are used for the preparation or for the manufacture of variety of new products which we use in day-to-day life. And for this synthesis, variety of reactions are used to build the framework of organic molecules. And let us see briefly the variety of reactions that are used to synthesize these new molecules. First, actually, we need to know all organic molecules, different reactions, different synthetic reactions mainly involve functionalization and functional group interconversion reactions. And what is functionalization? Functionalization is introduction of a functional group into a molecule. And you know, variety of substrates, organic substrates are there. What are they? Alkanes, alkenes, arenes, and heterocyclic molecules. So whatever synthesis, whatever reaction you do for the new synthesis or for the old synthesis, generally it falls into two categories, functionalization or functional group interconversion reaction. So let me briefly explain the functionalization of alkanes. It's very difficult to functionalize alkanes because they're quite inert, and mainly only few reactions are used, that is halogenation of alkanes, to synthesize some halo derivatives. Functionalization of alkenes. So this involves various reactions, and all these are very useful in organic synthesis. Why? Because alkenes can be made very easily in a chemical laboratory, and many of them are available from different sources also, and many of them are commercially available also. So when you are trying to functionalize alkenes, very important reactions you should think of are epoxidation, oxidation, hydroxylation, halogenation, and dehydrohalogenation, and catalytic reduction, and treating with hydrogen halides, and hydrolysis, hydroboration, oxidation, etc. So here in functionalization of alkenes, any alkene you take, you can epoxidize and prepare epoxides, that is oxidanes, which are again very useful building blocks for organic synthesis. Then you can functionalize alkenes by oxidation to carboxylic acids also. Carboxylic acids again can be converted to variety of new molecules, variety of intermediates, like for example, acid chlorides, acid amides, acid azides, and many more. You will be learning more about them in the later parts of this unit, okay? And functionalization of alkenes, you can do hydroxylation also. You can do cis hydroxylation, trans hydroxylation. And these diols you can prepare, the diols that you prepare by hydroxylation, again, are very useful as synthetic intermediates. Okay, and then you can do bromination, that is halogenation, bromination, chlorination, also you can do. For example, if you are doing bromination, you can prepare dibromo derivatives. For example, if you brominate propene, you can get 1,2-dibromo propane. And similarly, halogenation, other halogenation reactions. Okay, and suppose if you are doing dehydrohalogenation, what you will get? You will get alkynes. And again, alkynes are very useful intermediates for organic synthesis. See, alkynes, for example, you take styrene, you do dehydrohalogenation. What do you get? Phenylacetylene, which is very important raw material for variety of purposes. Okay, and you can functionalize alkenes. That means you can even reduce alkenes to different alkanes. So alkenes are easy to make, and conversion of alkenes into alkenes again will give you useful products. And you can add like hydrogen halides to alkenes to prepare haloderivatives. Here, see, Markovnikov rule, anti-Markovnikov rule, which you have already studied, will be useful to you to know the type of halo compound you are going to get, whatever starting material you are going to take. Okay, and next, hydrolysis. Hydrolysis also follows Markovnikov rule, and it will give you the hydroxy compounds, wherein hydroxy group an addition of OH, this addition of water follows Markovnikov rule, and then hydroboration and oxidation. So this gives less substituted alcohols. This is also one of the very useful synthetic reaction, and you can prepare in any amount of any number of derivatives by this simple hydroboration oxidation reaction. Also, just by taking appropriate alkene starting material and the reactions. Okay, and about reagents and all used, you will be learning more about little later. And then alkynes or another different types of substrates which are which can be functionalized very easily. See, you can prepare dibromoalkenes, you can prepare alkenes by just reduction, and that is catalytic hydrogenation, and you can prepare alkanes also by further catalytic reduction, catalytic hydrogenation of alkenes. Okay, and hydrolysis of alkynes gives you carbonyl compounds. So this again, carbonyl compounds are very important synthetic intermediates for the building, for building different organic molecules. And if you treat alkynes with a base, you will get alkynyl, acetylides. So again, which can be used in carbon-carbon bond forming reactions and many other purposes. So next substrate is benzene and other aromatic compounds. And you know pretty well, aromatic compounds undergo electrophilic substitution reactions, and a variety of electrophilic substitution reactions can be carried out on benzene and other aromatics. And taking simple benzene, so you can, from simple benzene, how many compounds you can prepare, you see. You can prepare chlorobenzene, you can prepare bromobenzene, you can prepare benzene sulfonic acid by sulfonation with SO3 and H2SO4, and you can prepare halobenzene by simple treatment with FeX3 and X2, and you can nitrate it. This is one of the very, very important reaction because nitro group is very much very easily made, and it can be reduced to amine, and it can be converted to a variety of other products which are used in organic synthesis. And Friedel-Crafts alkylation of benzene gives you acyl benzenes. And I've just taken benzene as a starting material, and you can prepare any number of derivatives from the products that are, for example, from acyl benzenes, if you can convert them into a variety of products. Nitrobenzene can be converted to different products. Halobenzene can be converted to different products. Benzene sulfonic acid again is used for a variety of purposes. And next, substituted aromatic compounds. Functionalization of substituted aromatic compounds. Here you see this functionalization reaction involves where you have an aromatic compound, and you have an aromatic compound. Functionalization of aromatic compounds involves substituted aromatic compounds involves. What are the substituted aromatic compounds? Generally, you think of amines, alkoxy benzenes, and halobenzenes, nitrobenzenes, acyl compounds, etc. Suppose if you are having an aniline, and aniline can be aniline can be converted to acetanilide, and which can be substituted, which can undergo nitration to give you para-nitroacetanilide. See here, we don't we are acylating this aniline to prepare para-nitroacetanilide. Why? Because aniline is a very reactive aromatic compound, and you cannot stop the nitration reaction at mononitration stage. Suppose if you want only mononitro derivative, we have to acylate and then do the reaction. And here, actually see the orientation effect of this acetanilide. It is ortho-para directing group. And if you have electron releasing groups on the aromatic ring, they will be ortho and para directing. If you have electron withdrawing groups on the aromatic ring, they will be meta directing. And aniline and amino group is an ortho-para directing group. Similarly, methoxy group, alkoxy group, any alkoxy group is an ortho-para directing group. For example, if you want, see, 4-methoxybenzaldehyde. So you have to start with anisole and do formylation reaction. And again, for formylation reaction, variety of formylation reactions are available, and that we will discuss at a separate place, because here only we are trying to see what all we can get from substituted aromatic compounds, what are the important derivatives we can get from substituted aromatic compounds, and the orientation effect of these aromatic compounds. So if you have in electron releasing substituent on the aromatic ring, you will be getting ortho-para substituted products. For example, here we are doing mononitration. So we have protected this group. And another reason is amino acids, because without protection, it will be protonated. And again, the reaction will not give you 4-nitroacetanilide. So acetanilide will give you para-nitroacetanilide. Similarly, you take any other substituted aniline, you will get corresponding 4-nitro derivative. Similarly, you take anisole. Anisole is methoxybenzene. In methoxybenzene formylation, we are doing Wilson-Manhart formylation, let us suppose, or any other formylation reaction. If you do, it will go to the formal group goes to 4 position. So you will get 4-methoxybenzene. benzaldehyde. So it need not be any sol. You can take any other alkoxy derivative. For example, instead of CH3, you can have here ethyl, you can have propyl, you can have benzyl. Any whatever alkoxy derivative you take, you will get 4 formyl, that corresponding alkoxy benzene. And suppose you have metachloronitrobenzene. Here you have 2 substituents. Chlorine is there, nitro is there. Chlorine is ortho-para-directing. Nitro group is deactivating. So deactivating and beta-directing. See, when you are doing metachloronitrobenzene nitration, what is it you are getting? You are getting the nitro group at the para position of the chloro group. That is, chlorine chlorine effect is dominating here. So you will get 3,4-dinitrochlorobenzene. Again, this is another useful intermediate. So for example, I have just given you 3 examples here. In this way, you can functionalize a variety of substituted aromatic compounds. And in this functionalization, mainly nitration, formylation, halogenation, and acylation. Acylation are very important. For example, here you have anisole. If you do Friedel-Crafts reaction on anisole, what you will get? You will get, for example, acetic anhydride and aluminum chloride. If you are taking, what you get? You will get 4-methoxyacetophenol. Instead of CHO, you will have COCH3. So like that, as depending on the size of the starting materials, you can prepare any number of products. So we have seen functionalization of alkanes, alkenes, and alkynes. And in these 3 alkynes and aromatic compounds. So in these 4 types, alkanes and functionalization of alkanes, generally we don't do. Only in rare cases and special cases we'll be doing functionalization of alkanes. Because all those groups, all those molecules can be indirectly obtained by other functional group interconversion reactions of other products. Whereas functionalization of alkenes, alkynes, aromatic compounds is very important synthetic reaction. Here I am going to talk about functional group interconversion reaction. So what do you mean by functional group interconversion reaction? The name itself suggests, what does it suggest? It suggests interconversion of one functional group to another functional group. Interconversion of one functional group to another functional group. And what are the functional groups, general functional groups you come across in organic molecules? Let us just list out them, important ones, only important ones. See, for example, nitro group, amino group, acid, carboxylic acid group, aldehyde, ketone, etc. See, I'm just trying to show you here how functional group of interconversion reactions of aromatic amines can give you a variety of products. How you can play with these interconversion reactions from aromatic amines to get the required product you need. For example, you are starting with any amino aromatic compound. What you can do? You can acylate it. You can prepare different acyl derivatives. For example, if you are taking benzene, means aniline, AR is equal. Suppose AR is phenyl, let us say, and you will get what you get? PHNHCO, and R is CH3, let us suppose. So acetanilide you will get. For example, if AR is toluyl group, corresponding amide you will get, and any other amine you will get corresponding amide. And it need not be COCH3, it can be CO another AR also. So for that AR, what we need to take here? AR COCl, means AR NH2 treated with AR prime COCl with aluminum chloride, Friedel-Crafts reaction. So, amide reaction here. It's not amide. It's just simple formation of amides. Acid chloride and aniline, you will get amide. So it can be anilide or amide, depending on the starting materials you take. Similarly, you can alkylate it. Means if you take alkyl halides you can alkylate it. And the reaction does not stop here. It can go to dialkylated and then trialkylated stage. That means through 3 moles of alkyl halide are used to prepare, to get trialkyl amine. So this reaction difficult to stop at dialkylamine stage because that is more reactive and it will further undergo with the reaction with the alkyl halide and gives you trialkyl and tetraalkyl. Actually, finally you will get trialkyl ammonium halides. Okay, that means quaternary ammonium salts. Okay, so that is the reason why when we are trying to prepare dialkyl derivatives, again we use indirect methods. Another, that is actually different reaction. We will learn when in that topic only. Okay, so you can alkylate it, and then you can prepare N-nitroso derivatives. See, N-nitroso, HNO2, by treating with NH2, HNO2, that is nitrous acid, you will get N-nitroso derivative, which can be reduced to corresponding amine. Okay, so here you see sulfonylation, and I suppose if you are treating with amine with aromatic amine with aryl sulfonyl chloride, what do you get? You will get a corresponding sulfonyl amide. Sulfonyl amides again are very important derivatives. Okay, and then this is another important reaction, diazotization. Diazotization reaction of aromatic amines followed by replacement with chlorine, bromine, iodine, fluorine, etc. It's really very important reaction. Very and it's many synthesis involve at some stage this reaction. See, any corresponding aromatic amine you take and you diazotize it, and that can be, for example, this is called ArN2 plus X minus. This is called diazonium salt. So this can be converted. You see the scope of this reaction. This can be converted to aromatic halides. X can be chloro or bromo by treatment with CuX2. Cuprous chloride will give you chloro compound. Cuprous bromide will give you bromo compound. And you can get a iodo compound also by treatment with Ki. And you can get even diazo compound, and you can, this phenol, it is treated with phenol, you can get diazo derivatives, azodide, you can, this is known as azodide, and then you can prepare, you can get hydroxy derivative, that is aromatic hydroxy phenols. From an amine, you can get a phenol. For example, you are taking aniline. Let us say you are taking aniline, and by doing this diazotization, you will get phenyl diazonium chloride that will be converted to phenol. So, for example, if someone asks you how aniline can be converted to phenol, this reaction is the best reaction. Okay, and even you can replace NH2 by the hydrogen. That means you can replacement of NH2 with hydrogen via diazonium salt is possible. H3PO2. See, this is also one of the very important synthetic reaction because aromatic compounds, these aromatic anilines can be made very easily. Means nitration followed by reduction. In any aromatic compound you take, you do nitration and then reduction. You will get a corresponding aromatic, amino aromatic compound. Okay, so that amino compound can be, it is actually activating the aromatic skeleton. So it activates the aromatic skeleton, and it can be used as such for the synthesis of variety of other derivatives. And once its job is over, you can even replace it with hydrogen. That means you are activating an aromatic ring, doing the reactions, and then deactivating, replacing it with hydrogen. That means you are removing the NH2. So after the work is done, you can remove it also. So this is another very important reaction in organic synthesis. And next, you can prepare diaryls. Diazonium, this is coupling reaction. Okay. For example, you take aniline here. So by this reaction, what you can get? Biphenyl. Suppose you are taking para-toluene. What do you get? Dimethyl, 4,4,4-dimethyl biphenyl. Okay. So that way you can prepare any number of biaryl derivatives. And this is another important reaction. See, Sandmeyer reaction. Actually, you have learned this in your previous classes in graduation and even intermediate. I think they must have taught you. Okay, you are already familiar with this reaction. I'm just showing the simple reactions, how they can be utilized to prepare innumerable number of derivatives, which can be useful intermediates in industry. Okay, see here, and which have got variety of applications. Diazonium salt, you can prepare cyano compound, nitriles. Okay, if you take aniline, again, I'm taking just aniline, but you can prepare benzonitrile. If you are taking toluene, what do you get? Tolunitrile, but this reaction. So diazonium salts are very, very important raw material, intermediates, which can be obtained from aromatic amines by a simple diazotization reaction. And it can be converted to, see, aromatic nitriles. And you can prepare even fluorocompounds. See, fluorocompound by diazonium salt treat with sodium NaBF4, and you will get this salt, which can be nitrated, which can be again replaced with nitro group, or which can be replaced with fluorine to give you fluoroaromatics. See how many reactions you can do by this simple functional group interconversion reactions. So this is the importance of functional group interconversion reaction. And any synthesis, big or small, whether you are doing a very big natural product synthesis or simple or any drug molecule, at least few of the reactions, few synthesis involve this aniline, amino group or diazo group as intermediates, or even nitrile or halogen or OH. So that is the importance of functional group interconversion reaction. So I have just shown you here functional group interconversion of amino group. How amino group is obtained? Amino group is obtained by the functionalization of nitration and reduction. That nitration to reduction to amino group is also a functional group interconversion reaction. So nitration is a functionalization reaction, and nitration to reduction to NH2 is a functional group interconversion reaction. So again, once you get an amino derivative and conversion into amides, conversion into sulfonamides, conversion into trialkyl amines, and conversion into diazonium salts, and by the intermediates of diazonium salts, you are preparing biaryls, you are preparing nitriles, you can prepare fluorides, chlorides, bromides, iodides, and phenols, hydroxy derivatives, and you can simply replace NH2 with the hydrogen, and unsubstituted NH2 is removed actually here, and this is very simple reaction. Otherwise, it's very difficult to remove NH2 from the aromatic ring. Okay, and then variety of other reactions you can do. Now, I am just trying to explain you other functional group transformation reactions. Here I have taken esters, acids. For example, acids, carboxylic acids can be made very easily from main substrates which are available, like alkyl benzenes, alkyl heteroaromatics. You can prepare this corresponding carboxylic acids by simple oxidation reaction. That is also another functional group transformation reaction. So once you have corresponding carboxylic acid, they can be bought or they can be made also. This carboxylic acid, see how many derivatives you can prepare from this carboxylic acid. You can prepare ester. you can reduce it to alcohol. And this ester also can be reduced to alcohol, primary alcohol. And carboxylic acid can be converted to amide. How? It can be converted to acid chloride and then treated with amine to give you amide. It can be converted to the acid chloride and it can be converted to aldehyde. That means acid chloride can be converted to aldehyde. Acid chloride can be converted to this diazomethane will give you COCH2, and this will undergo again a rearrangement reaction, which you will learn later in name reactions. So that is an M reaction, and it can be converted to one carbon homologation of acid. So one carboxylic acid is converted to another carboxylic acid by adding one extra CH2. Okay, and the COCl, it can be converted to azide. This azide can be reduced to amine. Again, this amine can be converted to variety of other products as I have shown you. Here I have taken it. R can be AR or it can be alkyl group. R may not be alkyl group. Here R can be aryl group also. Suppose if it is benzoic acid, what you can prepare by this series of reactions? Aniline you can prepare. Though we don't prepare aniline from benzoic acid, I'm just giving you an example. You can prepare any aromatic carboxylic, you can convert any carboxylic acid, any aromatic carboxylic acid to corresponding amino derivative. And you can prepare anhydrates also via acid chlorides. And this anhydrate, you can get amide. And again, amide, this elimination of reaction, you will get CN. And for this, all these reagents, different reagents are available, and which again form part of another units in organic synthesis. See, because organic synthesis is very vast, and I'm trying to just brief you what all you can do if you have one type of molecule. I mean, how many different reactions you can carry out and how it can be converted to a variety of useful products. See here, this is what I told you, carbon-carbon homologation. For example, you have here, let us just, as your benzoic acid, you are doing a reaction with benzoic acid. You can prepare benzoyl chloride. Then you can prepare this ester. Okay, so this by treating with diazomethane, and this can be converted to, what is this? It is phenyl acetic acid. So conversion of benzoic acid to phenyl acetic acid. And again, you do the series of reactions with phenyl acetic acid, the same series of reactions, you will get phenyl propionic acid. And similarly, again, it can just go on each time increasing one methylene, one carbon homologation. Okay, so this you will learn in detail at different unit. I think you have that also in your course. Okay, here, because I cannot go into details of all those reactions and mechanisms, because of my topic is only to teach you this type of methods, type of reactions used in organic synthesis. So functional group interconversion of acids and acid derivatives can give you how many. Just let us again briefly look at it. What are the products you can get? Suppose if you have a carboxylic acid, you can prepare ester. For example, you have benzoic acid. You can prepare methyl benzoate, ethyl benzoate, propyl benzoate, benzyl benzoate, like that. Okay. You can reduce it to alcohol. Suppose if you have benzoic acid, you can get benzyl alcohol. Similarly, other substituted benzoic acids you have, like paratolic acids you have, 4-methyl benzyl alcohol you can get. So like that. If you have N-acetic acid, like 4-methoxybenzoic acid, what you can get? 4-methoxybenzyl alcohol here. So like that. So R can be AR, or R can be R also. It can be CH3, like acetic acid. If it is acetic acid, if you use, what do you get? You will get ethyl alcohol. Though we don't prepare ethyl alcohol by this method, I'm just giving you an example. Okay. Here, another, similarly, amides. See, if it is pH, that is benzoic acid, you can get, and if R prime is CH3, you can get PHCO NHCH3, acetanilide, you can get, okay? And benzanilide, okay? And then it can be converted to corresponding acid chloride, benzoyl chloride. Okay, toluic acid, toluol chloride, N-acetic acid, N-acyl chloride, N-acyl chloride, phenyl acetic acid, corresponding acid chloride, and that can be converted to this is a reduction reaction. Again, in name reaction, you will get aldehyde. So benzoic acid to benzaldehyde you can make. Toluic acid to 4-formyl toluene, that is toluoldehyde you can get. So like that. Similarly, you have benzoic acid, benzoyl chloride. So is azide. So PHC, this is azide. Azide, again here, Hoffman rearrangement, Curtius rearrangement, very rearrangement reactions, name reactions you will know, you will get, and that can be converted to corresponding names. Okay. Now, here, but in this is another interconversion, important, very synthetically, very important interconversion reaction. It is conversion of alkenes to epoxides. Why I say it is important? Because alkenes are available from petrochemical sources and even commercially available, and it's very easy to prepare alkenes also. So that alkene, if you have, you can epoxidize it by using peroxides. So that epoxide can be converted to a variety of products by ring opening of epoxides. So you can open up the ring and attach many new groups to the carbon. So it is epoxides, oxidants are very useful in carbon-carbon bond forming reactions that we will learn in this course only, because that is a different unit. I am going to teach you that also in detail, how alkene epoxides, this epoxides can be converted to variety of useful products by CC bond formation reactions. Okay. Then removal of this here I need to tell you one thing, oxidation. Yeah, what is oxidation? Oxidation also actually makes use of interconversion reaction. So oxidation involves 4 types of reactions. One is addition of oxygen. This is also this is known as oxidation. So where we add oxygen, example, conversion of alkenes to epoxides. So we are adding an oxygen atom to the alkene. So this is an oxidation reaction. So if you get back this, again, that is not oxidation reaction. If this is conversion of alkenes to epoxide, is an oxidation reaction. And another type of oxidation reaction is removal of hydrogen. Removal of hydrogen. So is another type of oxidation reaction. See, alcohol is there. Alcohol is converted to, ethyl alcohol is converted to acetaldehyde. So what is that is happening here? One hydrogen from here, one hydrogen from here is going, and a double bond is formed to give you CHO. So removal of hydrogen from a molecule is also an oxidation reaction. Similarly, you see here, 2-propanol. 2-propanol, hydrogen is going from here and one hydrogen is going from here. So dehydrogenation, removal of hydrogen, dehydrogenation reaction. So what is that you get? Acetone. So conversion of propanol, isopropanol to acetone. Conversion of ethyl alcohol to acetaldehyde is an oxidation reaction. Here, what is that we are doing? We are removing hydrogen. Similarly, instead of ethyl alcohol, you just think of benzyl alcohol. For example, you have benzyl alcohol. So instead of CH3, you have PH. PH, CH2, OH. So what is the product you get? Benzaldehyde. So conversion of benzyl alcohol to benzaldehyde is which reaction? An oxidation reaction. This is also a functional group interconversion reaction. Why? Because you are converting alcohol functional group to aldehyde functional group. What is that we are doing? We are converting alcohol functional group to aldehyde functional group. Okay. So dehydrogenation reaction, this removal of hydrogen is an oxidation reaction. Again, oxidation reaction is very, very important in organic synthesis. So this way, benzyl alcohol you take, you get benzyl, phenyl acetyl, benzyl alcohol, you get pH CHO, benzaldehyde. Okay. Similarly, instead of CH3, you have pH CH2. That is phenyl, 2-phenyl ethanol. 2-phenyl ethanol. If you take, what do you get? pH CH2 CHO. That is 2-phenyl acetaldehyde you will get. So similarly, what you are doing here? Isopropanol. You are getting acetone. So let us assume that CH3 is removed, is replaced by pH. What is that? 2-phenyl ethanol. That is 1-phenyl ethanol. 1-phenyl ethanol. So 1-phenyl ethanol, what do you get? So this CH3 will be replaced by pH. That is acetophenone. So conversion of any alcohol. Primary alcohol will give you aldehyde. Secondary alcohol will give you ketone. So this is an interconversion reaction, and it has got a name, oxidation reaction, and that is also a very big branch of chemistry, oxidations. So by making use of oxidation reactions, you can prepare many important derivatives. And what is the other method of oxidation? It is removal of one electron from an anion. Let us take an example, phenoxide. Here, from phenoxide, we are removing an electron. So you will get phenoxy radical. So conversion of phenoxy anion to phenoxy radical is what reaction? It is an oxidation reaction. Similarly, substitution of one hydrogen by an oxygenated function. What are the important oxygenated functions? You have hydroxy group. For example, if you replace hydrogen by hydroxy group, that is also an oxidation reaction. So by doing so, in this reaction, for example, alpha to double bond. This is actylmethylene, acidic slightly. Okay, this replacement of this hydrogen is possible with hydroxy group. So here, what do you get? Allyl alcohol. Simply, if you add water to alkene, what you get? Alcohols. If you do allylic replacement, allylic hydrogen replacement by hydroxy group, we get allyl alcohols. And this is known as allylic oxidation. And this is also very useful synthetic reaction. Okay. So oxidation of alkanes and alkenes to form variety of organic derivatives. It is presented in the next part. Now, see, we have seen oxidation as addition of oxygen to the molecule. For example, alkenes to epoxide is an oxidation reaction, and it is a functional group interconversion reaction. What functional group you are interconverting here? Alkene. Alkene functional group is being interconverted to epoxy functional group. This is also an example of functional group interconversion reaction. As I told you, almost all the reactions will fall in these two broad categories only, functionalization and functional group interconversion reactions. Okay, so addition of oxygen is oxidation. Removal of hydrogen is also oxidation, and removal of electron from an ion to form radicals is also oxidation reaction. And the fourth one is substitution of one hydrogen by an oxygenated function is also an oxidation reaction. For example, here you have R is equal to CH3, R prime is equal to some other pH or any other group, you get corresponding organic molecule, allyl alcohol. Corresponding allyl alcohol you will get. Now, oxidation of alkyl side chains. See, this is also why I say this is important, because arenes, alkyl substituted benzenes are easily available raw materials from petroleum products, and they are very cheap also. So you can convert you can oxidize this side chains to corresponding carboxylic acid. For example, you want to prepare para-nitrobenzoic acid. Simply take para-nitrotoluene. And how you can get para-nitrotoluene? Toluene nitration. Though toluene nitration directly, it's very controlled nitration of toluene because toluene is quite reactive molecule and nitration it's very difficult to stop the nitration at mononitration stage. Though we have both methods available. Okay. See, oxidation of this side chain methyl group to carboxylic acid. So what is that you are getting? From para-nitrotoluene. Oxidation. Here's the oxidizing group is missing. Some oxidizing group actually in this. It's a simple carbonate and sulfuric acid is shown. It is the oxidizing group is missing. You said that different oxidizing groups are used. For example, here chromium trioxide is used. See that oxidation reagent should be used. Okay, you will get para-nitrobenzoic acid. So any alkyl, even with this lengthy alkyl chain also, it can be converted to corresponding acid. So here, for example, somebody asks you to prepare para-nitrobenzoic acid from toluene nitration, and then give you para-nitrotoluene, which can be oxidized to para-nitrobenzoic acid. And any others, like you have here any other group, you can have ethyl group, you can have all propyl group, you can have, and any other group you can. And how you can, for example, you have here chloro instead of nitro, chloro, and para-chlorobenzoic acid you want to prepare. So what is that you want to take? Para-chlorotoluene. How you can get para-chlorotoluene? You can get para-chlorotoluene by halogenation of toluene. Okay, so that para-chlorotoluene can be oxidized to para-chlorobenzoic acid. And again, once you have para-chlorobenzoic acid, as I told you in my previous slide, it can be converted to again variety of derivatives. So in the assignments, in the practice problems, we'll be doing some examples. Okay, so para-chlorobenzoic acid you have prepared, and that para-chlorobenzoic acid can be converted to para-chlorobenzoic chloride, para-chlorobenzamide, and so many other products which I have shown you, I think, in this slide. See, similar products you can prepare from that compound. So that is the importance of this side chain oxidation reaction, because alkyl benzenes are easily available, and they can be substituted with by electrophilic substitution. They can be substituted with a variety of functional groups, and once they are substituted, that alkyl side chains can be converted to corresponding carboxylic acids. So oxidation of alkyl side chains will give you acids, which again can give you a variety of other products. Now, see, we have seen complete oxidation here. CH3 is getting oxidized to corresponding complete carboxylic acid. And next, in the next slide, what is that we are doing? Controlled oxidation. See, controlled oxidation means you can stop the oxidation at intermediary stage. Means you can prepare aldehydes, for example, from alkyl benzenes. See here, chromium trioxide acetic anhydride in presence of acid will give you this diacetyl derivative, which can be hydrolyzed to diformyl benzene. See, this once you hydrolyze it, what do you get? Dihydroxy methyl intermediate, which will undergo dehydration very easily to form the pharmyl group. And another reaction is chromium, this CrO to Cl2 reaction, which will give you aldehyde directly. Okay, and this is another reaction, same example only, para-bromotoluene. You will get a complex here, and it will be converted to aldehyde. So similarly, this side chain CH3 chromium oxychloride and corresponding aldehyde derivative. Same. And here is partial oxidation, we call it. partial oxidation of alkyl groups, methyl group, can give you corresponding aldehyde. And as I told you, aldehyde again are very important intermediates. They can, functional groups actually, they can be converted to, for example, if you have CH4, you can convert it into CH2OH, you can convert it into COOH, you can convert it to shift bases, and you can convert it to many other products also. Okay. Grignard reagent, I mean, with Grignard reagent, you can get alcohols. So many reactions which you will know about in carbon-carbon bond forming reactions. Okay, they are useful, especially aldehyde substitution is very useful in the carbon-carbon bond formation reactions. Okay, and here, see, now another way to partially hydrogenate is side chain halogenation. You have to do ARCH3. So you will get monohalo derivative. For example, if it is toluene, you can get benzyl halide, benzyl dihalobenzene, and dihalomethyl benzene, and this can be hydrolyzed to give you dihydroxy compound as an intermediate, which will undergo dehydration to give you corresponding aldehyde. Similarly, here you see para-bromo, simply. Now, here I am taking bromo, para for bromotoluene, and you will take 4-bromo benzaldehyde. So controlled oxidation is possible, and you have, I have just shown you two reagents here, two reactions as an example, and you have many reactions, many reagents, which you might learn in detail in another unit. Okay. Now, oxidation with lead tetraacetate. This also gives you controlled oxidation only. Here you will get the corresponding benzyl alcohol. See, side chain CH3 is converted to first aldehyde and substituted. Halogenation you can do, corresponding benzyl alcohol you can do, and with lead tetraacetate you can acetoxy derivative you can get, and that can be converted to again corresponding benzyl alcohol, or even it can be used as such in some different reactions. So same here, bromination, side chain brominations, we always see CH2OH and distillation, acetoxy derivative with just different substitution. See, dehydrogenation of alkanes and alkyl groups. So this is also another oxidation reaction, as I told you, another important reaction. Here, what is it we are doing? We are doing dehydrogenation. Sorry, dehydration followed by dehydrogenation. See here, OH is tertiary alcohol, first dehydration, it will give you one double bond here, and treatment with palladium will remove hydrogen from here, So the driving force here for this dehydrogenation reaction is formation of an aromatic ring. So extended conjugation is there, and especially to an aromatic ring also, not only to double bond and the aromatic ring. So ultimately you are forming an aromatic skeleton which is quite stable. That is why this reaction is very facile. So by using powerful hydride abstracting agents like this type of reaction, hydrogen abstraction reaction, this hydrogen abstraction reaction, how to use hydride abstraction? Removal of hydrogen. So how we can do that reaction? By using powerful hydride abstracting agents. So two important reagents are there, chloranil and DDQ. Chloranil and DDQ will abstract a hydrogen from the alkane part. So that hydrogen is abstracted, and you will get this intermediate, and then a carbocation you will get. Carbocation you will get, and which is, if it is conjugated with another double bond or aromatic ring, it is stabilized carbocation. That's very easy to get. And then removal of proton will give you corresponding alkane. So what is this chloranil? This is chloranil. tetrachloro, this one compound, and this one dichloro dihydro, dichloro dicyano benzoquinone is DDQ. This is chloranil. Both are very important reagents for the hydride abstraction. Okay, so you will get corresponding aromatic. Actually, here also the driving force is formation of the aromatic ring from the reagent. So that is by abstraction of this hydrogen, you will get aromatic ring in the end. Okay. So for some examples, I am showing you here. See here, two aromatic rings are there. One here, one here. And this removal of abstraction of hydrogen from this is very easy. So once you abstract a hydrogen, once one hydride is abstracted from any, both are same only from here. So what you will get? A carbocation here. So benzyl carbocation, which is again stabilized. So just treatment with DDQ and diazine gives you the corresponding doubly bonded product. Okay, and see, I'm just showing you the importance of this reaction. Suppose you are trying to convert a ketone, see, cyclohexanone to a polyphenol derivative. Any other substituted one also you can take. For example, I'm just as an example, I'm showing you cyclohexanone. So how to convert to biphenyl by this type of reaction? See, treat it with the phenyl magnesium bromide. You know, treatment of ketones with the phenyl magnesium bromide will give you first the alcohol, and again it will undergo dehydration to give you this one. Okay, phenyl substituted cycloalkene. So here, phenyl ring is there and double bond is there, and extended conjugation is there. If this is treated with chloranil, so two double bonds are formed. So hydride is abstracted from here, hydride is also abstracted from there. So 2 moles of H2 are removed, and you will get a biphenyl derivative. This is a just representative example. You can have a fused benzene also, and a variety of other new products can be made by this reaction. So, another, this is also oxidation reaction only. See, substitution followed by elimination. You can get a double bond here, like dehydrogenation. It's ultimately what is that is happening? A dehydrogenation reaction only. So once hydrogen, this is hydrogen, is allylic bromination, we call it, and for that M-bromosuccinamide is the best reagent. So allyl bromide you get, and when it is heated with quinoline, and it will that dehydrobromination. So ultimately, what is happening here? 2 hydrogens, that is dehydrogenation is happening via substitution with bromine followed by dehydrobromination. This is also one of the important oxidation reaction and one of the important synthetically useful reaction. Okay. Allylic oxidation. So here, allyl position, double bond we are creating by substitution followed by dehydrogenation. Here also similar, see, and this is known as allylic oxidation because allyl group we are oxidizing. See, here also allylic oxidation we can do 2 ways, as I told you. N-bromosuccinamide bromination and followed by dehydrobromination. You can introduce a double bond there, that is ultimately dehydrogenation, and overall reaction is dehydrogenation. Here you see selenium dioxide. Selenium dioxide can be used to get the allylic oxidation product. Okay, so from alkene, allyl position is oxidized by making use of selenium dioxide. So here you see this methyl cyclohexene. How you can prepare this methyl cyclohexene? By like suppose if you take cyclohexanone, treat it with methane magnesium bromide, you will get corresponding tertiary alcohol, and dehydration reaction, you will get methyl cyclohexene. And treat it with selenium dioxide, you will get allyl alcohol, useful synthetic intermediate. Okay, and this can be even directly you can get, and selenium dioxide you can get alcohol, and sometimes the oxidation cannot stop at alcohol stage, you will get other product also here, ketone, or you can isolate it this and can be converted to ketone. So both the products may be obtained with the different ratios. Okay. So allyl alcohol, but controlled oxidation, you can prepare allyl alcohol by making use of selenium dioxide as a reagent. And next, what is the next reaction? Here you see cyclohexene treatment with acetate. Okay, acetoxate. This is simple substitution reaction, acetoxate, cyclohexene. And it can be removed actually to give you the double bond also, but it can be used to simply hydrolyze it to corresponding alcohol, allyl alcohol, which can be used to for organic synthesis. Benzylic oxidation. We have seen there allylic oxidation. Here, benzylic oxidation. So, benzyl position. What is benzyl position? The position which is attached to phenyl or other aromatic ring. This is benzyl position. Triphenyl methane, you see. Triphenyl methane, this H can be oxidized very easily. And with the chromium dioxide and acetic acid to give you this alcohol. Okay. And similarly here, ethyl benzene. Here, ethyl benzene. How you can get ethyl benzene? From, let us assume that you are preparing ethyl benzene from benzene. How you can get? Acetylation, Friedel-Crafts acetylation followed by reduction. So Friedel-Crafts acetylation is a functionalization reaction, and reduction to ethyl benzene is a functional group interconversion reaction. Okay, ethyl benzene, it is available commercially also. Ethyl benzene can be oxidized to benzoic acid. This is side chain oxidation, we have already seen. Okay, this, but benzylic position is being oxidized, so separately I have given an example. First, so benzylic position is oxidized, and further oxidation leads to benzoic acid. Okay, and chromium dioxide, this reagent is really useful for that conversion. And here you see, what is the benzylic position? This is the benzylic position. So KMNO4, if you use corresponding benzoyl substituted pyridine, you can get benzoyl substituted pyridine. You know, here this is also a very important reaction. Why? Because pyridine ring is electron deficient ring. You cannot do directly Friedel-Crafts acylation reactions. So, for example, you cannot treat it with the benzoyl chloride and aluminum chloride and do the reaction to get this 2-benzoyl pyridine. It's not at all possible. So that is the reason why we take corresponding benzyl pyridine and oxidize it. And once you have this, okay, once you have this benzyl benzoyl pyridine, it can be converted to again variety of products. This you can reduce to OH. This can be coupled with other amines to give different products. Okay, so that is the importance of this reaction. And another oxidation. This is also benzylic oxidation reaction. Pyridine carboxylic acid. So 4-methyl pyridine is commercially available. Simply oxidized. It's very easy to oxidize this to 4-pyridine carboxylic acid. So benzylic oxidation is also one of the key step, one of the important steps, important reactions used in organic synthesis. So, for example, I just you can have any other substituent here. You can get corresponding derivatives. So that is. This is again epoxidation. Epoxidation here of alkenes. This alpha beta unsaturated alkenes. This is electron deficient. So the mechanism of epoxidation is slightly different here. You can epoxidize with hydrogen peroxide, sodium hydroxide. This XO minus this atom because it's a allylic anion is stabilized by resonance. So you will get OH, and that anion attacks. And this card attacks here on OH. Okay. Oxidation. So, what are the oxidation reactions we have seen? Let us just what is oxidation? Addition of oxygen. But just briefly again, just revise whatever we have learned till now. What are the types of oxidation reactions we have seen? Addition of oxygen. Addition of oxygen is an oxidation reaction, and one important synthetic reaction is preparation of epoxides. So any alkenes you can take, you can prepare corresponding epoxides. Okay, and suppose if you take styrene epoxide, you will get any. Suppose you take substituted styrenes, corresponding substituted styrene epoxides you get. So addition of oxygen to any molecule, for example, alkene, gives you, and it is an oxidation reaction. And if you are adding oxygen to alkenes, it is oxidation reaction, and it forms epoxides. And I forgot to tell you one thing. It is a stereospecific reaction. Okay, it is cis epoxidation. You will get cis epoxides. Suppose if hydrogen, for example, if this hydrogen is replaced by methyl, this hydrogen is replaced by methyl, you will get epoxide, cis epoxide. Here CH3 and here CH3. If you take corresponding trans compound, you will get a trans derivative. Okay, addition of oxygen, and next removal of hydrogen. So we already seen removal of hydrogen from primary alcohols, you get aldehydes. From secondary alcohols, you get ketones. So removal of hydrogen is an oxidation reaction. And removal of one electron to form radicals. For example, from anion, one electron is removed and a radical is formed. This is an oxidation reaction. And substitution of one hydrogen by oxygen, oxygenated function. So one important functional group, which is oxygen, which we call oxygenated, is hydroxy group, and that substitution of hydrogen by an oxygenated function is also oxidation. So 4 important oxidation reactions: adding oxygen, removal of hydrogen, removal of one electron from anion, and removal of hydrogen. Okay, 4 types of oxidation reactions, and these are all functional group interconversion reactions. Okay, then controlled oxidation reaction. Side chain oxidation reaction. So any substituted aromatic compound you can take, and you can get corresponding carboxylic acids. Okay, we will be doing some exercises, then you will learn more about it. So, for example, I'll ask you a question here. Suppose if you have para-bromotoluene here, what is the product you get here? Para-bromobenzoic acid. Suppose if somebody wants you to prepare para-bromoacetamide, So, or para-bromo-benzophenone. Let us say para-bromo-benzophenone. How you can get? Para-bromo-toluene you take. Para-bromo-benzoic acid you prepare. From that, para-bromo-benzoyl chloride you prepare. And just do Friedel-Crafts reaction with benzene. So, para-bromo-benzophenone you get. Okay, like that. So, controlled oxidation, as I told you, this side chain is partially oxygenated to aldehydes. Okay. And we have seen oxidation with electric triacetate. This is also controlled oxidation. It will give you benzyl alcohol, benzyl acetate, and from the alkyl side chain, methyl. And the dehydrogenation of alkanes, like this. This is very important because, see, you can hear it. What I have prepared here? Methyl naphthalene. Suppose if you want to prepare phenyl naphthalene, how you can get it? So you take corresponding, see, instead of CH3, you should have pH here. How you can get that? So from the corresponding carbonyl compound and phenyl, magnesium halide, you will get tertiary alcohol, and that can be dehydrated, followed by dehydrogenation with the palladium to give you this phenyl substituted naphthalene. So I'm just giving you an example. You can prepare phenyl, toluene, any other group here by taking corresponding tertiary alcohol, which in turn can be prepared from the corresponding carbonyl compound and Grignard reagent. This is by using powerful hydrate abstraction reagents. You can do dehydrogenation. I said the two important reagents are chloranyl and DDQ. They are very useful in extending the. I mean, if you are creating a double bond in conjugation with the already existing double bond, a double bond or an aromatic ring, this reaction is very easy because the driving force is that extended conjugation, the stability obtained from that extended conjugation, and the aromatization reaction. Okay. So this mechanism we have seen. Allylic oxidation. Allyl position is being oxidized by making use of NBS or selenium dioxide. These are the most common reagents used for this purpose. So intermediates in allylic oxidation. What are the? This is proposed intermediates. Okay. These are the intermediates. And the removal of this one. Selenium. These are the proposed intermediates. Okay. Benzylic oxidation, we've already seen. Oxidation of alkenes. And some more examples. With examples I am showing you here. Epoxidation. See, epoxidation of alkenes is oxidation. And here, how they are epoxidized? Treatment of alkene with a para-acid will give you this complex, which will give you finally epoxides. It's a stereospecific reaction, I said. Here you see R2 and R4. One side, R1 and R3, and the other side you see in the epoxide ring, R2, R4 one side, and R1 and R3 another side. So this para-acid is generally generated in situ. In situ means in the same reaction. They are unstable, they cannot be stored. So we have to generate it in situ. How do you generate it? From the corresponding carboxylic acid and hydrogen peroxide. So in the reaction flask itself, they have generated, para-acids are generated, and they are treated with alkene to give you corresponding epoxide. So these substitutions can vary. R1, R2, R3, R4 can vary. So variety of substituents are possible and a variety of epoxides can be made. And the importance of that epoxidation reaction is, as I told you already, epoxy ring can be opened with different substituents like Grignard reagents, and other organometallic reagents, and it is very useful intermediate in the carbon-carbon bond forming reactions. So you can prepare a carbon-carbon, you can prepare your choice, products of your choice by choosing the corresponding epoxide and corresponding organometallic reagent. This will be in fact learning in detail in carbon-carbon bond formation reactions. Okay, and see here you see trans diphenyl, trans C position, you see phenyl groups are in trans position. So this is a stereospecific reaction. Epoxidation is a stereospecific reaction. So a trans compound, you get trans. If you get cis compound, like phenyl group is this side, let us say. Instead of trans, if it is this side, you will get phenyl this side. Okay. And here you see, this is cis. So the corresponding epoxide is also cis. If you take trans, it will be trans. Here you see. Here, this is an extended conjugation. I showed you the mechanism. HOO minus attacks, and then that O forms a methoxide. This is not stereospecificity, not that much as in this case. It's not a stereospecific reaction. So epoxidation of electron deficient alkanes with paracids is relatively difficult and requires heating. You know, this is a simple reaction. In fact, does not require heating. It's quite alkanes are quite reactive because they are electron rich. But if they are conjugated with electron withdrawing groups, what happens? They become electron deficient because some of the electrons are drawn towards this electron withdrawing group. So like this it will go. So here this we will generate an electron deficient carbon center here. So that will be attacked by HCOO, HOO minus that which is again OH is eliminated to give you the corresponding epoxide. So it's relatively difficult. However, we can still make it by heating. Here no need of heating. See, 20 to 30 degrees, 0 to 5 degrees. And the more reactive, if it is more reactive, you don't need higher temperatures at all. Whereas this electron deficient alkenes are in fact less reactive. So you need heating. You need to heat. And this metachloropurbenzoic acid, MCPBA, is only one reagent per acid, which is quite stable and which can be used, actually which is normally used, which can be stored. Whereas other paracids are prepared in situ. And this paracid is quite unstable and it can be even stored. And this is used generally for electron deficient, for the epoxidation of electron deficient alkenes. Okay, so you get epoxide here, and then so this is the mechanism we told you. This is the mechanism. OH is attacks, and this is stabilized anion, and again OH minus is eliminated to give you the epoxy compound, especially in case of alpha beta unsaturated carbonate derivatives, esters, etc., because they are electron deficient because of this stabilization, because resonance. Another oxidation, synthetically useful oxidation reaction, is formation of diols. So how, from where they are formed? Formation of diols from, again, alkenes. This is indirectly oxidation of alkenes only. Okay, so oxidation of alkenes either by using KMnO4 or osmium tetroxide can give you diols. So if you're using KMnO4 osmium tetroxide, you will get a cis-diol. Cis-diol. It's also a stereospecific reaction. So this is just a broad general reaction. A manganese ester is formed, which is the hydrolyzed dihydroxy compound. See, again you see, it's a stereospecific reaction. I said R1, R2, R3, R4. R1, R3 one side, R2, R4 another side. So you are getting a manganese ester where R2, R4 one side, R1, R3 another side. Simply hydrolyzed. Again, same thing. Stereospecificity is retained. Okay, this is so you will get 1,2 diols, which are again very useful intermediates in organic synthesis. And the next, see, cyclohexene, you will get 1,2 alpha, OH, one side, same side, okay, KMnO4. And KMnO4, here also you see OH, X, okay. So it's a very important reaction. KMnO4, you will get same type of products. Osmium tetroxide also you get same type of products. I'm just showing you this with osmium tetroxide. Here I have shown you manganate with permanganate. Here you see the intermediate involved is this osmic ester. This again, this is also a stereospecific reaction. You see R1, R3 one side, R2, R4 another side, and you are getting intermediate which will be converted. Diode will be converted. This would be okay. Similarly, here you see OH. So ethyl group is alpha and OH other osmium ester is forming from the is attacking from the other side, beta side, and after hydrolysis you will get beta diol. So in the examination, it's very important, you know, this stereospecificity. So the opposite to the bulky group, the osmium tetroxide attacks. It will not be attacking from the same side of ethyl. It will be attacking from the opposite side. So you will get sterically less similar side to osmium tetroxide attacks to the alkene. Okay, so you will get cis 1,2 diol. Okay, so this is formation of diols. For example, I asked a question here. You take ethyl cyclohexene. If you take any benzyl, let us say, benzyl cyclohexene, what you will get? If you treat it with osmium tetroxide, this alpha position, benzyl will be there. Means PHCH2. Okay, phenyl methyl. That is benzyl. Okay, benzyl 1,2 diol. So this hydroxylation of diols is very important reaction. Another question, though I cannot get the answer here, I'll give you an exercise later, which you can send it to me later. See here, suppose if you want, if you want to convert a cyclohexanone to this compound, the one which is here. How you will convert cyclohexanone to with ethyl magnesium bromide lutate? Then you get an alcohol here, tertiary alcohol. So dehydration of that will give you this double bond. Okay, this double bond. And the treatment with the osmium tetroxide or KMnO4 will give you ethyl group here. Alcohol. Sorry, this one to diol. So instead of ethyl, you can have methyl, you can have benzyl, you can have a group of your choice. So this is the formation of diols. So we have seen in this today's lecture, what all we have seen. Let us just summarize. Let us summarize. We are building molecules. Okay, what mean we are trying to build the molecules, construct the molecules. How? Functional, by making use of various functionalization and functional group interconversion reactions. So as I told you, functionalization is introduction of a functional group. Functional group interconversion is conversion of one functional group to another functional group. So we have many substrates, alkanes, alkenes, and alkynes, and we have seen various functionalization reactions of alkanes, alkenes, and alkynes. Okay, and arenes also. So different derivatives we have seen, different molecules, how you can prepare, and how even substituted arenes. And then functional group interconversion reactions of amines we have seen, and functional group interconversion reactions of carboxylic acids and esters we have seen. And then what we have seen? Oxidation and reduction. Oxidation reactions we have seen. We have not seen reduction, that will be in next class. So oxidation reactions, what is oxidation? Addition of oxygen is oxidation. And removal of hydrogen is oxidation. And removal of electron is also oxidation. And the substitution of hydrogen by oxygenated function is also oxidation. Okay. And then we have also seen oxidation of alkyl side chains to give carboxylic acids, which in turn can be converted to a variety of products. We have also seen controlled oxidation of alkyl groups to give corresponding aldehydes. We have seen controlled oxidation with beta triacetate, bromine, and that is NBS also we have seen, and selenium dioxide also we have seen. And this dehydrogenation, removal of hydrogen, also we have seen, which is an oxidation reaction. And removal of hydrogen, two types: catalytic dehydrogenation and dehydrogenation with chloramine and DDQ, main important ones which are industrially used very often. And this is substitution followed by elimination reaction by making use of NBS, allylic bromination followed by dehydrobromination to introduce a double bond. Ultimately, it is removal of hydrogen. That is also oxidation reaction. So we have seen intermediates in allylic oxidation, and we have also seen benzylic oxidation, how it can be converted to a variety of important products. And oxidation of alkenes, that is epoxidation, we have seen, and we have seen formation of diols, that is cis dihydroxylation. Okay, what is remaining is only trans dihydroxylation, which we will take up in the next class. So time is up, and hope you have understood. And if any doubts are there, you can give the organizers my mail ID and my phone number. You can contact there. Okay. Thank you.